Kyle. This is Mr. Yeager with physics, looking at energy in particular. We're going to look at a couple topics today. This is more of an introduction to energy. We're going to look at what is energy, what are types of energies out there. In physics, we focus on really two types for this unit. There are a couple other types we're interested in, but I'm going to kind of share general versions of energy, types of energy. We're going to look at this concept of work. Oh, and of course I hit the wrong thing already. We're going to look at the concept of work and then the conservation of energy. Again, just briefly at this time. Power is also on this, so that should be included too. We're going to look at power. So this is more just the introduction to the terms, to the formulas, and a little bit of how they're used. And then the next lecture is more on more detailed ideas of work with another one following that on conservation of energy particularly. So, energy itself, okay? Energy, as I usually tell everybody, is a fairly tough topic because it's very abstract. It's something we can't really grasp, okay? But, we're going to say energy is this ability to cause a change. Another definition that's very common for it is it's the ability to do work. And again, this work is the scientific work I'm about to discuss, so that still doesn't even make much sense. What I can really say energy is energy is the ability to do anything. Without energy, you are dead. But the thing is, even when you're dead, your body still has some stored energy. It's basically you don't exist at all once the energy is completely gone. Okay. So it's the ability to cause any type of change, to do any action, whatever you're thinking about, to cause any change in what's going on with that object. Energy has to be used. So there's all sorts of types, and most of these types we're actually not going to discuss, but you probably have heard these back in physical science. Okay? There's mechanical energy, basically the energy of motion, that's what's behind that. Okay? Chemical energy, energy from atoms, or bonding of atoms. Thermal energy, that's basically heat. We got electrical energy from electrons. We got nuclear energy from the nucleus of an atom. There's light energy, there's kinetic energy, there's potential energy. There's all these different types, but they're all energy. And the thing is that I always try to really hammer in is they're all measured in joules. They are all energy. They can all do some sort of work, cause some sort of change. All we're doing is adding an adjective to describe how we are, in a way, I guess, seeing that energy at that time, or describing where is that energy coming from. Probably that would be the better definition, to say in detail where that energy is coming from. But thermal energy is still energy just like nuclear energy is. It's just the difference is where it's coming from. Okay? Everything's measured in joules. So, in physics, we're going to primarily focus on two types of energy, at least especially in this early unit where we're still talking about motion. And the first type is kinetic energy. And I'm again assuming that you probably have already heard of this if you're in a physics course. You've heard of it sometime even before physics. It's the energy of motion. It'll depend on an object's mass and velocity. Okay? So when either one of these increases, the kinetic energy increases. I'm going to show you a formula later to clearly show you that mass and velocity are used to calculate kinetic energy. But if I look at this quick example, if I go, which of these objects has the most kinetic energy? Well, it would be the one that's the fastest and the one that's largest. In that case, would be the truck. Even though it's the same speed as the motorcyclist, the 80-kilometer-an-hour motorcyclist, we can obviously assume the truck is much more massive. So the 80-kilometer truck would have the most kinetic energy. The slower motorcyclist would have the least amount of kinetic energy. When an object is in motion, it has kinetic energy. All right? It has some amount of kinetic energy. It doesn't matter whether it's speeding up, slowing down, or moving at a constant speed. If it is moving, it has kinetic energy. The second type out there, the second primary type, is what we're going to talk about called potential energy. Again, from a standard definition, you probably have heard this is stored energy. This is the more vague type of energy because you're not going to really be able to see it or know that it's there until it's obviously released in some form. All right? That's why we call it potential. It has the potential to be used in another form, to convert to kinetic energy or whatever. All right? The other way we look at it is potential energy will depend on the position or configuration of the object. In this unit, we are primarily going to be looking at the idea of the position of the object. And what we call that is gravitational potential energy. All right. This is one that's based on, we can see with my example here, it's based on height. How high up is the object? If the object is off the ground, there is the potential that it can fall, and as it falls, that energy changes into kinetic because it goes faster and faster. It has that potential to obviously move. If the object's on the ground, it doesn't have any potential to move unless somebody actually physically pushes it in some form. Configuration, we're not going to talk about this one so much this unit. This one's based on the idea of, we're going to talk about springs in a later unit. And this would be the idea that if you push a spring in, obviously what does it want to do? Push back out, okay? So if you basically, deform that spring, stretch it or squeeze it, it wants to return to the way it originally looks. So that's what we're looking at with potential energy. So we're going to usually label this as GPE, gravitational potential energy, is what we're going to look at in this unit. So kinetic energy and gravitational potential energy. Which boulder has more gravitational potential energy? Obviously the one that is higher. Okay. What other ways can we store energy? Like we said, springs, chemical, electrical. There's lots of different ways you can store, but the only one we're going to be looking at in this unit is gravitational. All right. So here are your formulas. Kinetic energy is 1/2 mv squared. All right. You can see our units. Mass has to be in kilograms. You cannot plug grams into this formula. It has to be in kilograms. Velocity, that's always going to be in meters per second, and that's going to be, you're not going to have to convert that one. All right. But it's 1/2 mv squared. You are only squaring the v. All right. Common math errors is people, one, forget to even square it. Two, I'll see people do 1/2 mv parentheses squared. No, no, no. Okay, that's not the formula. So 1/2 mv squared. Okay. So that is kinetic energy measured in joules. Then we also have gravitational potential energy measured in joules because energy is joules. Joules, it doesn't matter what type of energy, measured in joules. And potential energy is mgh. mgh. Okay. Mass times gravity times height. Nothing squared there. Just multiply all three together. But there is one thing we should notice here. Okay. M times G. We've learned that from force. M times G is weight. So gravitational potential energy is also weight times height. So if they give you the weight of the object in newtons, all you have to do is multiply that by the height in meters. If they give you the mass, multiply it by 9.8 and then multiply it by the height. All right, same thing. So weight times height is mgh. This leads us to work. All right. With work, the standard definition is it's the transfer of energy through motion. All right. This is how you give an object energy. All right. You're not creating energy, you're giving it from yourself. But this is how you give or transfer energy to another object. You must exert a force over a distance, exerted through a distance. And that's why we have our formula, work equals force times distance. All right, now there's another version of this. We're going to learn that in a later lecture. All right, but work is force times distance. I just want to give you a heads up now. Work is measured in joules. That means work is energy. And so the way to kind of think about this, and I'll try to add more again in a later lecture, is work is what gives an object gravitational potential energy when I lift it. Okay? If I lift an object, I'm applying a force upwards and I'm moving it a distance upwards. As you can see here, the distance must be in the direction of force for work to be done. If I push an object that's on the ground, I can give it kinetic energy. So what I'm trying to say is work creates, again, I don't like using that word, or I should say gives an object gravitational potential energy, or gives the object kinetic energy, or technically it takes it away. Okay? So work causes a change in energy when you apply a force over a distance. Force times distance. Okay, distance has to be in meters. So if we do a quick problem here, what you see here is we have somebody that's carrying a backpack. It weighs 30 newtons. That's the weight. So what are you going to have to use to hold that backpack? What force? You're going to have to apply 30 newtons. Okay, if we look at what's given to us. We're going to have to, if we want to lift the backpack, I need to apply at least a 30 Newton force. All right, it would basically be, go back to our free body diagrams, weight down, force applied up. If you want to lift it, you'd have to lift it with at least 30 newtons force. How high are you lifting it? 1.5 meters. That's your distance. All we got to do is, I'm not even going to talk about the triangle. Okay. All we have to do is just plug it in. Force times distance, 30 times 1.5 is 45 joules. When you lift that backpack, what type of energy is this? If the backpack's on the floor and you're lifting it into the air, we are now above the ground. You're giving it gravitational potential energy. The backpack now has gravitational potential energy. Okay? Where did it get that from? From the work you did. If we do another quick one. A dancer lifts a 40-kilogram ballerina 1.4 meters in the air, so somebody's lifting this ballerina up, and then holds her and walks forward. So they're holding her up, straight up, force pointing up, but then they walk forward for 2.2 meters. So this is going to be a good example here. How much work is done on the ballerina during and after the lift? So if I look at what's given again, the mass of the ballerina is 40 kilograms. I'm going to have to change that to weight because it has to be a force being applied. During the lift, I lift her 1.4 meters, and then we carry her 2.2 meters forward while she's up in the air. Okay? So what we have to do here is we have to first find the force. How much would you have to use to lift her up in the air? Well, that would be her weight. Force would be 40 times 9.8. So this ballerina is 392 newtons, and so therefore I need to lift with 392 newtons to get her up in the air. So during that lift, I applied 392 newtons for 1.4 meters, and therefore I am giving her 549 joules of energy. Again, what type? Potential, because she's now up in the air. All right, so that was just the lift. What about afterwards? Well, afterwards, okay, there's going to be some terrible pictures. Okay, if you're holding them up in the air, it looks like they're holding a baby, but whatever. If you're holding them up in the air, you are applying a force upwards, but then you walk a distance perpendicular to that. If we go back to the definition of work, force and distance have to be in the same direction. They're not in the same direction. So guess what? You don't do 392 times 2.2. That would be incorrect. The answer to this would be there is no work done after the lift. The answer would be 0 joules. You're not changing her position in the air. Their position is exactly the same the whole time as you're walking forward. All right? Now, some people go, I thought they're moving, so don't they have kinetic energy now? You have kinetic energy. You're doing work on yourself making your move, not on the ballerina. The ballerina is just staying in place and moving along with you. So there's an important point to make here. All right? Work is not always done when there's a force and a distance. Work is done, I'll write it out here real quick. Okay. Yep. So work is done when force and distance are, I'm going to say parallel. I'm going to be a little bit more specific. What that means is that the force and distance have to be in the same direction. Okay? Work is done. Or force and distance have to be in opposite directions. We will learn work is also done. So these are examples of work. All right? But work is not done, and there's usually two very common scenarios. One is pretty obvious, the other one's not. Let's do the not obvious one first. When you simply carry something, all right? When you are carrying an object, no work is done. All right? Because the idea is you are applying a force upwards but moving forwards. So they're not in the same direction. Okay? No work. The other more kind of obvious example, okay, you get to see some more of my awesome pictures, is if I push a wall. Okay? If I push a wall, I can apply a force, but does the wall move? Okay. Of course not. Okay. The wall will not move. So clearly, work equals force times distance. Force times 0 is 0. So what I'm trying to say there is work is not done if object doesn't move. Okay? So the object has to move in order for work to be done. Okay, so let's finish on up here. We got only like 2 more slides real quick. Some I'm going to skip. All right. So just to briefly introduce the law of conservation of energy, energy cannot be created or destroyed. It can only be changed to another form. All right. We're going to be doing a lot more problems with this, but the idea here is if I hold an object up in the air, okay, if I'm holding an object up in the air, it has gravitational potential energy. If I let it go, it's going to obviously fall. It's going to move and it's going to change into kinetic energy. If I give the object 10 joules of gravitational, by the time it hits the ground, it'll have 10 joules of kinetic. I can change what type it is, but I can't change the overall amount that I have. The whole time that object has 10 joules of energy, but it's just what type of energy it has can change. All right, so that's the potential of the kinetic energy example. All right, I'm going to skip these. These are just kind of simulations. This leads us finally to the idea of power. Okay, and power is the rate at which work is done. It is measured in the watt, which is a joule second, but you can say watt. Watt would be big W. All right. The formula for it is work divided by time. This is work, not weight, divided by time. Time has to be in seconds, work in joules. The thing is, you're going to get plenty of problems where I'm not going to give you the work, I'll give you the force and the distance. Obviously, multiply those 2 together and divide by time. That would be power as well. All right. So basically, the last example might be something like this with power. Power, you really only need to kind of go, how do I calculate it? And maybe, can I just interpret who has more power? Okay. So if I do a quick problem with this, all right. What if I have basically 2 people going up a large hill? Okay? And this hill has a specific height. If we have 2 people, these are identical people, they have the same mass. Okay? If they get up to the top of this hill and I say, who did more work? Who did more work? The answer would be, the work would be the same. And that confuses some people because they go, wait, shouldn't it be easier for this person to go up, the one in the steeper? No, not necessarily. Same as the one going flat, but they have to work longer. Still doesn't matter. The idea is they both reach the same height. So what type of energy do we have? We have gravitational potential energy. Who has more gravitational potential energy? Once again, it's the same. Because they're at the same height, they're the same mass, they're on Earth, mgh. So work is the same. But what if I said that the person on the left took 10 seconds and the person on the right took 5 seconds? Who did this with more power? This is person A and this is person B. All right, in terms of power, B would be greater than A because they did it faster. Work done in less time. Work done in less time. All right. So that would be another type of example you might see, and that's where you're practicing on some of the worksheets you'll be doing. All right. Thank you very much.